According to Newton, light consists of tiny particles. So these are tiny particles, and the color of the light depends on size of these particles. Whenever the size of the particle changes, according to Newton, color also changes. So under these particles comes out from a source, any source, just like bullets comes from a gun continuously. Now, according to Newton, speed of light is greater in denser medium and it is less in rarer medium, but afterwards it is proved wrong by other scientists. Now after this, according to Huygens wave theory of light, Huygens wave theory, this is Newton's corpuscular theory, because he named this particles as corpuscles. So this is corpuscular theory, and Huygens wave theory states that he explained the properties of light by taking the wavefront. So before that, according to this wave theory, light is a mechanical wave. That means it requires a material medium for its propagation. So medium is required according to Huygens, and it is also longitudinal wave. Longitude, that is wave is moving like this, particles also vibrates in the same direction, but this is wrong because light does not require any medium for its propagation and it is a transverse wave. So these two are wrong. So after that, Maxwell proposed that light is a electromagnetic wave, that is a non-mechanical wave. So what is this electromagnetic wave? Non-mechanical wave means it does not require any medium, and according to Maxwell wave theory, light is a transverse wave. And here Huygens proved that speed of light is more in rarer medium and less in denser medium. So speed of light is more in rarer medium than in denser medium. Example, speed of light in air is 3 into 10 power 8, and the speed of light in any other medium is less than 3 in 10 power 8, and so this is proved by Huygens. And Maxwell is the first scientist to give a formula to find the speed of light in a medium, or this is the speed of light in vacuum. According to this, as it is an electromagnetic wave, that means light consists of both electric and magnetic field vectors. So he gave the speed of light in terms of permeability and permittivity of free space. But in any other medium, this is going to be 1 by root over mu epsilon. So this is the speed of light in any other medium other than vacuum or air. Now, so after this, Maxwell proposed this in around 1865. Now according to this, suppose if you take the electromagnetic wave, we know that already we studied this in electromagnetic waves here. These are the electric field vectors, and these are the magnetic field vectors, which are mutually perpendicular to each there, and the direction of the electromagnetic wave is in this direction, which is perpendicular to both electric field as a magnetic field. Here electric field is in xy plane and magnetic field is in xz plane, and electromagnetic wave is traveling along x-axis. Now the electric field vectors are responsible for vision. So electric field vectors of a light are responsible for vision here, and also responsible for the effect shown by the light. So electric field vector are responsible for vision, So a magnetic field vector is responsible only for the propagation of light. That's why while representing a light, we will represent only the electric field vector. So then it is a pure transverse wave only. If you represent only E bar of electromagnetic wave, then it appears as a transverse wave, pure transverse wave only. But this is the wave due to a single atom. But any source which is producing electromagnetic wave will have different atoms. So these closely packed atoms, that may be a bulb or a fluorescent lamp, anything, different atoms vibrates differently in different directions. So the electric field vectors are because of the vibrations produced by these atoms. Let us say this atom is vibrating in this direction, this is vibrating in this direction, this is vibrating in this direction, this is vibrating like this. So different particles vibrate in different modes here or different directions. Now, if you combine all these electric field vector vibrations, now you can draw this as first one is like this, second one is like this, third one is like this, fourth one is like this, fifth one once again like this, sixth one like this, seventh one like this, eighth one like this, ninth one, 10th one, 11th one, so 12th one. So this is how you can represent unpolarized light. This is called unpolarized light. So what is meant by unpolarized light? The light in which the vibrations are possible in all possible directions. So this is called unpolarized light. But you can see these are all field vectors here. Now let me take any 4 or 5 here, 4 or 5 vectors. Let us say these are the electric field vectors here, but this vector can resolve into 2 components here. So you can remove this one because already we resolved this into 2 components. This can also be resolved into 2 more components here along x-axis and y-axis. Even this can resolve into 2 components, and even this can also resolve into 2 components. So as a whole, the same diagram, if we resolve each and every electric field vector along x-axis and y-axis, and this is the simple way of representing unpolarized light. So both this diagram same, only thing is all the field vector which are neither acting along x-axis or y-axis are resolved along x and y-axis, so that this is a unpolarized light. But what is a polarized light? Here the field vectors are combined to different directions. If field vectors are, these electric field vectors are confined to a single direction, then this is called a polarized light. Unpolarized light, the light that is coming from a bulb, the light coming from a sun, these are all unpolarized lights. Now, how to represent unpolarized light, and what is this unpolarized light? A light beam which is having vibrations in more than one plane is known as unpolarized light. Here, if you take a light which is having vibrations in all possible directions, this is called unpolarized light. So in this case, if you take this, resolve this into 2 components along x-axis and y-axis here, resolve this into x-axis and y-axis here, resolve this along x and y-axis, resolve this into x and y-axis, then this is called unpolarized light. This is called unpolarized light. Now this is the front view of the light which is coming towards us, because these are the electric vectors, these are electric vectors, light is coming like this. So the front view of this one is like this. But if you see from this side, the same light can be seen like this. This is the electric field in this direction, this is the electric field which is into the board. So here unpolarized light consists of 2 types of vibrations. One is arrow components, the other one are dot components. What are these arrow components? So arrow component indicates the vibrations which are vibrating in the plane of the paper. So arrow components, plane of paper, dot components, perpendicular to plane of paper. But if you observe this polarized light, a light beam which has vibrations only one plane. So either only the arrow components or only dot components, and this light will indicate a polarized light. How to convert this unpolarized light into polarized light? Now let me take, this is the unpolarized light coming from a source here. And when this light is allowed to pass through a calcite crystal, and this is the calcite crystal, this is called a crystallographic axis. So when this light passes through this one, the vibrations are in two different directions here, because all the electric field vectors are resolved along x and y axis, and finally we can represent this light like this with only arrow and dot components. Now the crystallographic axis will allow only those vibrations, this is the direction of light, only those vibrations which are parallel to its path axis. This axis is also called path axis of the tourmaline crystal or nickel prism or calcite crystal, ice pear. So these are all the substances which converts this unpolarized light into polarized light, or nickel prism is also one of those examples for polarizers. So now the light will come out with only one type of vibrations. That means it will allow only the arrow components and it will block the dot components. So the path axis will allow only the arrow components and the dot components will be stopped by this one. So this is called unpolarized light, and this is called polarized light. So in this type, if the intensity of the unpolarized light, let us say this is I naught, as half of the vibrations are stopped or restricted by this crystallographic axis of these polarizers, and the intensity of the polarized light is exactly half of the intensity of this unpolarized light. So this is the polarized light here, and whose intensity is equal to I naught by 2. Now in Malus law states that whenever unpolarized light is passed through a polarizer here, this is called polarizer, and this is another polarizer which is used to test the whether it is polarized or not. So this is used to analyze the polarized light. That's why this is also called analyzer. So this is another polarizer which is used to analyze this light. Now if you allow this light here, this as the path axis is parallel to these vibrations, now the light will come out as it is, and the intensity will be I naught by 2. But if you rotate this crystal here such that the path axis is perpendicular to the path axis, the first one, then no light will emerge from this one. That means if this crystal is rotated such that this path axis is perpendicular to this, if these two are perpendicular, also called cross polarized, and you won't get any light here, so emerging light intensity will become 0. So according to Malus law, the intensity of the light that is emerging from the analyzer depends upon the angle between these two, and also the intensity of light that is emerging from the polarizer. So intensity of the light that is emerging from the analyzer directly proportional to the square of the cos angle between polarizer and analyzer. Let us say this is the polarizer, and let us say this is the analyzer here, which is inclined at an angle here. So this is the angle between these two. So depending on this angle, if this is 90, cos 90 is 0, no energy, no intensity will come out. Now this, based on this one, we can write the intensity of light that is emerging from the analyzer equal to the actual intensity between these two, that is intensity of the polarized light, into cos square theta. So this is the very important formula for polarization. In Malus law, the intensity of the light that is emerging from the analyzer. So this is analyzer here, analyzer, and the first polaroid is called polarizer here. So Malus law states that intensity of the light emerging from analyzer is directly proportional to square of the cosine angle between polarizer and analyzer. Now here, this is the polarizer, this is the analyzer. So this is the unpolarized light. So unpolarized light has an intensity of I naught here. So after passing through the polarizer, we know that only the arrow components will be allowed here. The dot components will be selectively absorbed by this polarizer. It will not allow this dot components to enter into the other space, as this pass axis will allow only the vibrations which are parallel to this one. So the intensity of this one will be I naught by 2 here. So this is the polarized light. Polarized light. So what is the maximum intensity of polarized light in this Malus law? So maximum intensity of polarized light, so we call it as I max here. This is I max. Now here Malus law states that intensity of the light emerging from the analyzer directly proportional to cosine square of the cosine angle between polarizer and analyzer, and that also depends upon the maximum intensity of the polarized light. So now by combining these two, I directly proportional to I max cos square theta, so I is equal to I max cos square theta. I am not talking about the unpolarized light intensity here. This is the maximum intensity of polarized light, which is equal to I naught by 2. So this is a Malus law. Generally, when this light is taken for unpolarized light, I naught is equal to k into a naught square. When it comes here, the intensity, maximum intensity of the polarized light is given by I naught by 2, which is equal to a naught by root 2 whole square. So if the amplitude of the unpolarized light is a naught, what is the amplitude of the polarized light? This will be a naught by root 2. So amplitude of polarized light, this is maximum amplitude of polarized light is a naught by root 2. But here, if it is a naught here, this is a naught by root 2. So this is also a naught by root 2 cos theta. So this will be a naught by root 2 cos theta here, because if it is a naught by root 2 at an angle, if you resolve this one into this one, this will become a naught by root 2 cos theta. So what is the intensity of this light? The intensity of this light is equal to some constant into a naught by root 2 cos theta whole square. So I is equal to k into, this is a naught square by 2 cos square theta. But what is a naught square by 2 here, which is nothing but I max? So this can be written as I is equal to some constant k 1 into I max cos square theta. So this is the amplitude of the wave or polarized light that is emerging from analyzer. Amplitude of polarized light from analyzer is given by a naught by root 2 cos theta, where a naught is the intense amplitude of the unpolarized light, a naught by root 2 is the amplitude of polarized light, a naught by root 2 cos theta amplitude of the light that is emerging from the analyzer. Methods of producing polarized light. We have different methods, but we are interested only in this method as well as this method here. We can produce polarized light by reflection as well as refraction, and also double refraction, dichroism, scattering using nickel prism as well as by using polarides. Now, these polarides are the materials which are having the molecules aligned themselves in a particular orders. Molecules aligned in a particular order. Now, how to produce polarized light by using this reflection method? So it is observed by Malus and explained by Brewster. So in this case, if you take a denser medium here like water or glass here, if a incident light ray incident on this surface which is a unpolarized light here, that means it consists of both dot and arrow components. So this is unpolarized light. So after incidenting on this one, some part of the light will reflect and remaining part will refract through this medium here. So it is observed that when this angle of incidence is gradually changed, here we will have these dot components as well as some arrow components. Here also we will have some dot components and some arrow components here. But if you change this angle of incidence slowly, if you increase this angle from 0 to some value at a particular angle of incidence called polarizing angle, this is also polarizing angle, you will have only the dot components. So reflected light will have only dot components. So previously it was a semi-polarized light, but at this particular angle this is called a polarized light, whereas this light consists of all arrow components with some dot components here. That means this is a semi-polarized light. And it is also found that in this condition the reflected and refracted light rays are mutually perpendicular to each other. So now what we can write, this is the refractive index of this medium, this is the polarizing angle, this is the refracted angle. From Snell's law we can write 1 into sine theta p, where polarizing angle is equal to n into sine r. But the sum of these three angles must be equal to 180 because this is the normal here. On the normal, theta p plus 90 plus r is equal to 180. Theta p plus r is equal to 90, or r is equal to 90 minus theta p. So now I am going to write sin theta p is equal to n sin 90 minus theta p. Sin theta p is equal to n cos theta p. So n can be written as sin by cos, that is tan theta p, which is known as Brewster's angle. So this is called Brewster's angle. So Brewster's law states that this is also called angle of polarization or Brewster's angle, and the statement is called Brewster's law. The refractive index of a medium is equal to tangent angle of polarization if reflected and refracted light rays are mutually perpendicular to each other. So this is called Brewster's law. So Brewster's law states that refractive index of a medium, that is n, is equal to tangent angle of polarization if reflected and refracted light rays are mutually perpendicular to each other. So when these two are mutually perpendicular to each other, in this condition the reflected light ray will be completely plane polarized. So in this condition reflected light ray is completely plane polarized. Plane polarized means it will have vibrations only in one plane. Here this is perpendicular to the paper. The plane is perpendicular to this paper. For water, the polarizing angle, if you want to find out a polarizing angle, we know that N water equal to 1.33. Now, according to Brewster's law, N is equal to tangent angle of polarization. 1.33 is equal to tan theta p. So, theta p is equal to tan inverse of 1.33. So, angle of polarization will be around 53 degrees for water. Similarly, for glass, we know this value is 1.5 and angle of polarization for glass is equal to nearly 57 degrees. Now, if we arrange glass plates like this, and if the light incident on this one at an angle of 57 degrees here, if it is 57, this is the normal here, so light incidence, now it will be 57 degrees, and this is a completely polarized light. But the light which is entering into this one will converge here, that means it will move towards the normal here. So now if you arrange so many glass plates here, a pile of glass plates, and it is found that after arranging 32 glass plates, the light which emerges after refraction is also plane polarized light. That means it will have only dot components and it will have only the arrow components here, because all the dot components here, it has some dot components also in this diagram. All these dot components will be reflected from the different surfaces, and this is called a pile of plates, pile of glass plates, and the emergent light after refraction will be a plane polarized light. So this is how you can produce a polarized light by refraction. And the third one, by dichroism. There are some crystals like calcite crystals, quartz crystals have the property of selectively absorbing one type of vibrations and emitting or releasing the other type of vibrations. That property is called dichroism. So dichroism is selective absorption of one type of vibrations of light. Now, in scattering, when then light is entering into the atmosphere from the sun, and it is a unpolarized light, this unpolarized light will have both the arrow and dot components. Now, it is found that when it enters into the atmosphere, these are the air molecules, and the air molecules will have some electrons, and due to the collision between these two, light will scatter in all possible directions here. So it is found that the light which is reflected by an angle 90 degrees is completely polarized light here, whereas the light which is traveling in the same direction remains as unpolarized light. This remains as unpolarized light only. But this light, this is a completely polarized light. This is a unpolarized light, and these are semi-polarized. That means it consists of both arrow and dot components here. So these are semi-polarized lights. So after that, by using Nicol prism means if you add two calcite crystals with the help of Canada blossom, then if you send the light, it will also produce the polarized light. Then by using the polarized, already we discussed this, by using the terminal crystal we can produce, in Malus also we discussed about this point. Now in the double refraction, similar to this one, if it is the unpolarized light having both dot and arrow components, when it enters into this one, here instead of one refraction, there will be two refractions, and one light ray will undergo total internal reflection, and the other one will emerges out. So this light which emerges out, and which one which is undergoing this TIR, actually this diagram should be like this here. When it undergoes this one refraction, it will undergo total internal reflection, and other one will come out as it is. Here the light ray which obeys this laws of refraction is called O ray, that is ordinary ray, and the other one which will not obey the laws of refraction is called extraordinary ray. So here we have double refraction, two refractions. So here also it is found that it consists of dot components and it consists of only arrow components. So you will get two types of polarized light.